So last session, we learned about trees, about decision trees, and these are really powerful methods, and at the same time, they're really explainable. And one application why explainability matters is that, let's say you apply for a loan or a mortgage, and the bank is gonna make some decision and either approve your loan or mortgage or not approve it. But then it's not game over. If they don't approve it, they need to tell you why they rejected your application. And the reason for the rejection couldn't be that you're too old, or it couldn't be that the color of your skin is that color. That's why we didn't approve your loan. Or because of your gender, we denied your application. So it has to be interpretable. The machine learning framework that you're using, and it shouldn't be looking at features that are sensitive, and it shouldn't make decisions based on those. It could make the decision based on your credit score or because you didn't pay back your loan, etc., on time, but it couldn't be based on your age. That's why being interpretable matters. And decision trees are really interpretable, and that's why they're being used in practice so often. And that's why some of these companies that have to explain to their customers their decisions, they are reluctant to use deep neural networks or other less interpretable but more powerful methods. So decision trees, linear regression, logistic regression, they are interpretable. So there is this idea, we learned about decision trees, there is this idea of bagging or boosting. And it says that if you have your data set, that's your entire data set, and you sample from it with replacement, that's going to give you multiple new data sets that you can work with. So you sample a data set having the same size as your original data set, but now your samples are with replacement. That's why you're going to end up with different data sets. And you can take that data set and apply different machine learning frameworks on it. If your machine learning framework is a tree or a bunch of trees, that's going to be called a random forest. The randomness is coming from your data sets being random. These are random subsets of random samples of the same data set. And it's a forest because you have multiple trees. And the idea is that you can have weaker decision makers, but if you have many of them and each one is voting and we let the majority to win, we are going to get a very powerful machine learning technique. It is not interpretable, or is not as interpretable as a single tree, but it's really powerful. It's going to be a powerful classifier. And the idea is very similar to democracy. A lot of people, if they make a decision together, that should be a good decision in the end. And the package that we are going to use for that is library random forest. You need to install it. And then once you install it, you can load it with the library command. And then its usage is very similar to before. You have random forest. We are doing classification, and we are trying to explain the cut variable based on the rest of the variables in our diamonds data. So our data is diamonds, and we are still doing classification. It's going to take some time because each time it is sampling our data set, it's creating a new data set, it's training a tree for that data, then it samples another one, it trains another tree, etc. But the cool thing is that these operations can be done in parallel. All of these, you first sample your data, and then you can do these in parallel. And then the decision is when you synchronize your methods. So it took a while. It's done now. Now we can look at our model, and it's reporting the confusion matrix for us, but we are gonna compute that ourselves. The prediction took a while because it had to push it through multiple trees, entries, and then vote. So the prediction took a while, but then we can look at the confusion matrix as before, and it's around 78% accurate. So let's compare this to a single tree that was 70% accurate, and let's compare it to a deep neural network. This was support vector machines. Support vector machines are also a powerful method. They're 75% accurate. This was a deep neural network. It was 79.9. And I guess this was the best result that we had. This one was 58% for Naive Bayes, we had 93, but this is for iris data. And then we had 65. It was for multinomial logistic regression, and this one was k nearest neighbor. So decision trees or random forests are also really powerful. There are multiple trees making a decision, and they're going to give us very good results. It's 78% accurate. Any questions so far? Okay, great.